Hello, everybody. This is 5.3, the fundamental theorem of calculus. So everything we spoke about comes together to this theorem, and you'll see it in a minute. The fundamental theorem of calculus, kind of abbreviated as FTC, is named, of course, because it establishes the connection between the two branches we've seen, which is the differential calculus and the integral calculus. And it gives the precise inverse relationship between these two parts. So, the story we built on the whole time, from the basic tangent example, area under the curve example, until we got into the differentiation, until we got to integration, and these FTC bundles the two and gives us the connection between the two, right? And you see it. So before we do that, let's see a function defined by a definite integral. The first part of this FTC is this part. We need to define this for the first part of FTC. So if you have a function f of t, be continuous function defined on some type of closed interval ab, if x varies between ab, we can define the function g by having g of x equal to integral from a to x f of t dt. Sometimes this function g is called accumulation function because it gives the area accumulated so far up to x. And we'll see a graph. Let's show a graph here. So if, just to explain it in a way, if it happens that f of t is positive, means above the x-axis, it's going to represent, of course, the area under this curve. And you see x being here between a and b. So the area accumulated up to x, that's what it calculates. And you have a and b, and of course f of t and t. So this is a nice picture to show the connection between a and b, x and f of t and all that. So what is this theorem of calculus? And this fundamental theorem of calculus is two parts. So let's look at the first part. Here is the, let's call it theorem T in C1. Now that function we defined with the definite integral, if a function is on that closed interval AB, then the function is defined by this, and x is between a and b, and the function, of course, is continuous, f of t on AB, and differentiable on the open interval AB. We have g prime, which is the first derivative, equals f of x. That's the first part of this theorem. The second part, and I'll explain it in a minute, is the second part here, which follows easily from the first part. It provides us with a much simpler way of doing this. This integral is equals to f of b minus f of a, where f is the antiderivative of f, that is a function such that f prime, of course, equals f. So we transition from part one to part two. So part two makes it easier to calculate. And of course here we're using a definite integral, and the c constant is not showing, but we'll see when we get to indefinite in different section. So briefly, what happens? You have part one, a function g of x, which is such that integral a to x f of t dt Of course, x is in between a and b, and g prime is the derivative of f of x. So this means that if you integrate this function f of t, it gives you a function such that g of x, such that g prime of x is f of x. The second part, which makes it easier to calculate, it just says f of b, this capital F, minus f of a using these limits, upper and lower limits of the integral, where f is the antiderivative. So if you want to calculate an integral, you need to find its antiderivative. And don't forget about the properties we did in the previous section. And once you find that, you can use the upper and lower limit. And Leibniz, of course, had this notation that d to dx of the integral equal f of x, right? So which says that f is integrated and then the result is differentiated. So you see this inverse relationship between the differentiation and the integral, and that's what this FTC does, and that's how the story between the two problems kind of closes, right? All right, so let's look into some examples. Here is a summary of it to know what part one is and what part two is. So for example, here if it just says use part one of the fundamental theorem of calculus to find the derivative of the function, of course, it just means that g prime of x is going to be equal to this inside here using the x square, the x, which means here 4x squared minus 3x. So this is part one. This integral is g of x such that, right here, such that g prime equal f of x, and this is f of t, so x takes the place of t. It's just direct, no calculation, just to understand this part. And of course, now if you want to move on with part two, then means you need to find the antiderivative of it. The upper limit is 4 and the lower limit is 2. The antiderivative of 5 is 5t. For 2t is t squared. For 3t squared is t cubed, right? Such that if you differentiate, right? If you differentiate here with respect to x, you should get this f of t here. Okay, then we just use the upper and the lower. So you'll have the 5 now with the 4 minus, and now you're going to do with the 2. So you just need to watch for the numbers there, right? So 20 minus 16 plus 64 minus 10. Now that's going to be a plus 4, and that's going to be a minus 8, and that comes up to 54. So similar thing you'll do here for this integral. You want to find the antiderivative of this, which is negative cosine theta. And these are the limits. We know with the multiple thing for the properties, you can do this. So now you can use cosine pi minus cosine pi over 4. And Cosine pi, that's a -1. Cosine pi over 4 is square root of 2 over 2. Now we get the negative inside. It's going to be 1 plus square root of 2 over 2. Okay. So the method you learned in differentiation, now you're going to use here because you're reversing it to find the antiderivative first. So maybe we can do that this is 4 over this, whichever way you're going to think about it. If you want to think about it this way for this one and this one, this, right? You can think about it that way. And so now from the properties we saw that with this you can do this way. And even the 4 as well can come here. So now the antiderivative for -3, this power here, is going to be that plus 1, right? Which is -2. And that's going to be and this one did and it's going to be 3 and 2. And of course, these two are positive, so they'll work without the absolute value. And 4 over -2, that's -2, this one, which means 1 over u squared, 3 over 2, plus here we can use for the 3, then use for the 2, you know, the f of b minus f of a, right? That's a -2. So 1 over 9 minus 1 over 4. And remember, if you have two logs and they're subtracted, you can combine them as a quotient there. So this is times 4. This is times 9. That's a 4 minus 9 over 36 plus ln e halves. So -5 times 2 is a 10 over 36 plus ln e halves. And that's we'll simplify 5 over 18 plus ln e halves. Okay. So remember the properties of the integrals you're going to use to here to bring them to a form that is easy to, you know, to find antiderivative. And after that, you can use part 2 for evaluation of the integral. Thank you.